AP Statistics videos for Chapter 3 and 4. The first question we have is a basic AP Statistics question. It says, here are Professor Moore's times in minutes to swim 2,000 yards and his pulse rate after swimming in beats per minute for 23 sessions in the pool. I have written down the data, time, pulse, time just keeps going, pulse just keeps going. The first thing we need to figure out is to verify that a linear model appropriately models the data and state the equation of the linear model. Well, this we're going to use our calculator for. Our calculator instructions, first we're going to plug in all the data, which I have already done. Then we're going to go to Stat, Calc. We're going to go down to the linear model, number 8. Make sure our X-list is L1. You can get second, L2 for the Y. Hit calculate. To find the correlation of our data and proving that it is an appropriate model, we're looking for an R squared. And we want the R squared to be as close as 1 as possible. So we're going to write down that for the linear R squared is 0.5564. Go out 4 decimal places. Then we want to make sure the linear model is the best. So we're going to go to the other models, Stat, Calc. We're going to go down to Exponential, Calculate, and Exponential was R squared of 0.5468. Alright, let's try the power one. We know that rules out exponential because it has an R squared lower than linear. And we're looking for the R squared closest to 1. So power has an R squared of 0.5475. Obviously, linear has the highest. So we're going to erase exponential and power, keep that linear R squared. We need to get back to the linear information so we can find our equation. Let's go to 8. Make sure we have L1 for X, L2 for Y. Calculate. Linear regression equation is Y equals A plus BX. Our calculator gives us all our information. We have Y equals A, 479.934 plus B, negative 9.694x. There's our equation. Let's go ahead and box that. Now, I'm going to go ahead and erase the data since you've already seen it and you already know it's plugged into your calculator. Then, I'm going to go ahead and write our linear line once again at the top. We have Y equals 479.934 plus negative, plus and minus, just make minus. X. We can cross this out since we know we're correct. Part B says, the next day's time is 34.30 minutes. Predict the professor's pulse rate. His actual pulse rate was 152. Well, our pulse rates were our Y's. That's what we put in L2 of our table, our Y's. So, we're trying to find the prediction of our pulse rate, Y. We can plug in the time we've been given for X, since we use time as our x's, and that was 34.30 minutes. Here we can use our calculator once again. We're going to go ahead and plug that whole equation in. 479.934 minus 9.694. Make sure you put a parentheses to do the multiplication here. And you get Y equals 147.4298. So that's our predicted pulse rate. Predicted pulse rate. his actual pulse rate was 152. So how accurate was our prediction? Our prediction was 152 minus 147.4298 was 4.5702 below actual. Now we can go ahead and erase this again. We're going to keep our equation up here. We might need it again. Part C says, suppose we were told only that the pulse rate was 152. So now we've been given the x. You now want to predict the swimming time. Find the equation of the least squares regression line that is appropriate for this purpose. What is your prediction? How accurate is it? Well, now we want to flip around our equation because we're looking for the time, not the pulse rate anymore. So we need to flip around our least squares regression line because time and pulse are on different scales. So to do this, we're going to go to Stat, Calc, we're going to go back to our LinReg. But this time, instead of having L1 as our X list, we're going to make it L2 by pressing second L2. For Y, we're going to do second L1. We're going to calculate, and we're going to get our new equation, which is going to be Y equals A is 43.0972 plus BX minus 0.0574. It's a negative X. Now we're going to plug in our new X's, which is time, and we're going to get Y equals our new time, it gives us is, or our pulse rate is a new X's. So our pulse rate is 152. So let's do 43.0972 minus 0.0574 times 152. And we get Y equals 34.3724. What is our prediction? How accurate is it? Well, we know the actual time was 34.3. So, we're really close. We're only 0.0724 above our predicted or actual time. Alright, let's erase all this. So the last question says, explain clearly to someone who knows no statistics why there are two different regression lines. Well, time and pulse are on different scales. Time we have in minutes, and it's around 34, 35, 36 for each one. And pulse we have in beats per minute, and it's a bunch higher numbers, 152, 153, more than that, less than that. So they're on totally different scales. So when we flipped our equation, we flipped the x and y, and we basically flipped the graph over. And when you flip the graph over, you could have a graph that goes this way on a graph like this. But if you flip the x and y's, our graph might go this way. So now we have a totally different least squares regression line than a strong positive this way or a strong negative over here.